Bales of hemp and manila fibers arrive at the rope factory. Raw materials from distant plantations that will be twisted into the heavy cordage essential for maritime vessels and industrial applications. Workers comb the coarse fibers through hackling equipment, separating and aligning the long strands needed for strong rope construction. The enormous rope walk stretches hundreds of feet through the factory building, its extreme length necessary for forming continuous rope strands through the twisting process. Steam-powered machinery turns massive wheels that twist multiple strands together, creating heavy ropes capable of supporting tremendous loads on sailing ships and industrial equipment. Inside this steam-powered rope factory, twisted fibers transform into heavy cordage through systematic twisting, tarring, and laying processes that define industrial rope manufacturing in the 1850s. If you could leave a like and subscribe to the channel, it would really help this project continue bringing historical industrial content. Thank you for your attention. Now back to the video. Raw hemp and manila fibers arrive at the factory receiving area, imported from tropical plantations where these plants are cultivated specifically for their exceptionally long and strong fibers suited to rope making. These natural fibers possess characteristics ideal for cordage production, with lengths reaching several feet and tensile strength sufficient to create ropes that can support immense weight when properly twisted together. Workers unload the compressed bales, checking documentation that identifies fiber origin, grade, and the processing already completed at the plantation or initial preparation facility. Each bale undergoes inspection for moisture content and quality, as excessive dampness promotes rot, while poor fiber quality would compromise the strength of finished ropes. The receiving warehouse accumulates substantial fiber inventory, organized by type and grade, to ensure proper material selection for different rope specifications ranging from light lines to massive cables for naval vessels. This systematic material management ensures the factory can produce diverse rope types while maintaining the quality standards essential for applications where rope failure could cause serious accidents or costly cargo losses. Before rope making can begin, the raw fibers must undergo hackling, a combing process that separates, aligns, and removes short broken fibers unsuitable for quality rope production. Workers feed fiber handfuls through hackling machines equipped with progressively finer metal teeth that comb through the material repeatedly, straightening fibers and removing impurities caught in the plant material. This mechanical combing produces fiber that flows smoothly and aligns uniformly, essential characteristics for creating consistent rope with predictable strength properties. The hatchled fiber emerges considerably cleaner and more organized than the tangled raw material that entered, with short fibers and debris removed through the aggressive mechanical combing action. Workers gather the prepared fiber into loose bundles called slivers, organizing the material for the spinning stage that will create the yarns, forming rope's basic structural elements. The hackling room fills with fiber dust and debris that workers must manage constantly, as the aggressive mechanical action breaks some fibers and creates airborne particles requiring ventilation systems to maintain acceptable working conditions. The prepared fiber now moves to spinning equipment, where twisting creates the yarns that will be further twisted into strands and ultimately into finished rope. Workers feed the hatchled fiber into spinning frames that rotate at controlled speeds, adding twist that binds individual fibers together into continuous yarns of specified thickness. The direction of twist matters significantly in rope construction, with yarn spinning typically following one direction, while subsequent strand and rope twisting proceed in opposite directions to create balanced structure, preventing unwinding. Steam power drives the spinning machinery through overhead line shafts and belt systems, sustaining the continuous rotation necessary for producing the substantial yarn quantities required for industrial rope manufacturing. The spun yarn accumulates on large bobbins, with workers constantly replacing full bobbins with empty ones to maintain production continuity throughout operating shifts. This spinning stage transforms loose fiber into structured yarn possessing considerable strength, though still far weaker than the multi-strand ropes that represent the final product after additional twisting and compaction stages. Many rope grades undergo tarring, a treatment process that dramatically improves water resistance and prevents rot. making the cordage suitable for maritime applications where constant moisture exposure would quickly degrade untreated natural fibers. Workers immerse yarn bobbins or loose fiber bundles in large vats of heated tar, typically coal tar or pine tar, heated to fluid consistency that enables penetration throughout the fiber mass. The tar saturates the yarn, filling spaces between individual fibers and creating a protective barrier that prevents water from reaching the cellulose fibers that would otherwise absorb moisture and decompose through bacterial action. The tarring process creates the characteristic black color associated with traditional naval cordage, with the dark coating also providing protection against ultraviolet light degradation that would weaken untreated rope exposed continuously to sunlight. Workers must carefully control tar temperature and immersion time, as excessive heat damages fibers while insufficient treatment leaves inadequate protection against moisture and rot. The tarred material emerges sticky and black, requiring thorough drying before proceeding to rope-laying stages where the treated yarn will be twisted into strands and ultimately combined into finished rope. The tarred yarn undergoes drying in heated chambers or outdoor drying yards where air circulation removes excess tar and allows the coating to cure into a stable protective layer. This drying stage may require hours or days depending on environmental conditions and the amount of tar applied during the treatment process. Workers arrange the yarn systematically during drying to prevent tangling or adhesion between adjacent materials that would create handling problems during subsequent processing. The dried, tarred yarn displays the characteristic stiffness and dark appearance of treated cordage, significantly different in handling characteristics compared to the softer, lighter-colored untreated yarn used for lighter ropes not requiring water resistance. The rope walk represents the factory's most distinctive architectural feature, an extremely long, narrow building or corridor where the actual rope formation occurs through controlled twisting of multiple yarn strands. These structures often extend 300 to 500 feet or more, their extraordinary length necessary because rope making requires space for the full rope length during the twisting process that gradually shortens the material as twist is applied. One end of the rope walk houses the stationary machinery, including a large wheel or drum that holds and rotates the rope strands, while the opposite end contains a movable carriage that travels toward the fixed end as rope formation progresses. Workers prepare the rope walk for production by attaching multiple yarns to hooks on the rotating drum, with the number of yarns determining the strand thickness and ultimately the finished rope diameter. Steam-powered machinery drives the rotating drum that twists the attached yarns together, with controlled rotation speed determining the tightness of twist applied during strand formation. As the drum rotates, the yarns twist together, creating strands that are the intermediate structural elements eventually combined into finished rope. The strand twisting process requires workers to maintain even tension across all yarns, preventing some from being tighter than others and creating strength variations that would compromise rope quality. Multiple rotating drums may operate simultaneously for factories producing several rope types concurrently, with each rope walk dedicated to specific rope specifications. The strand formation continues until the desired twist density is achieved, producing strands that possess significantly greater strength than the individual yarns from which they're formed, due to the twisting action that compacts fibers and creates friction between elements. The laying process represents the final major stage, combining multiple strands into finished rope through additional twisting that creates the familiar helical structure characteristic of traditional rope construction. Workers attach completed strands to a laying carriage that moves along the rope walk while rotating to apply the final twist that combines strands into rope. The laying typically twists in the opposite direction from strand formation, creating balanced structure where the opposing twist directions prevent the rope from naturally untwisting under load or when tension is released. A cone-shaped device called a top travels with the laying carriage, guiding the strands together and ensuring they combine evenly into the forming rope, rather than tangling or separating unevenly. Steam power provides the substantial force necessary for laying heavy ropes, as the twisting action creates significant resistance that would exhaust human workers attempting to power the process manually. The laying carriage moves slowly along the rope walk, with the rope gradually forming behind it as the process progresses toward the fixed end. The rope emerging from the laying process displays the characteristic twisted structure that gives traditional rope its strength and flexibility, with the helical arrangement of strands creating a structure capable of bending around sheaves and drums while maintaining high tensile strength. Workers inspect the forming rope continuously, watching for irregularities or tension variations that might indicate problems requiring process adjustment before significant rope length contains defects. The finished rope accumulates at the rope walk's fixed end, where workers guide it through coiling equipment that winds the completed cordage into manageable coils for storage and shipment. The rope manufacturing process demonstrates how simple twisting operations, when performed systematically with proper materials and controlled conditions, create products possessing mechanical properties far exceeding their constituent materials' individual characteristics. Heavy ropes for naval or industrial applications may undergo additional processing, including serving, where thin cord is wrapped tightly around the rope surface to provide additional protection against abrasion and water penetration. This serving process creates a smooth external surface that runs more easily through sheaves and reduces wear compared to the rougher surface of unserved rope. Workers apply serving using specialized equipment that rotates around the rope, wrapping the protective cord in tight spirals that cover the underlying rope structure completely. The served rope displays dramatically different appearance compared to bare rope, with the smooth wrapped surface contrasting sharply with the characteristic helical structure visible on unserved cordage. Quality inspection focuses on rope diameter consistency, strand uniformity, and overall construction quality that determines load-bearing capacity and service life in demanding applications. Inspectors measure rope diameter at multiple points along its length, verifying consistency within specifications and checking for thin or thick spots that would indicate construction problems. The rope is examined for proper twist density, as insufficient twist creates loose rope lacking strength, while excessive twist makes the cordage stiff and prone to kinking. Visual inspection identifies surface defects, broken fibers, or irregularities requiring correction before the rope can be approved for sale. Load testing may be performed on sample sections, applying measured force to verify the rope meets strength specifications for its intended application category. The finished rope is coiled systematically for storage and shipment, with proper coiling technique essential to prevent kinks or damage during handling and transport. Workers employ specific coiling methods depending on rope size and type, creating coils that can be moved easily, while preventing the rope from developing permanent bends or twists that would impair its performance. Each coil receives identification, marking indicating rope diameter, length, type, and intended use category, enabling customers to select appropriate cordage for their specific applications. The warehouse accumulates diverse rope inventory, ranging from small diameter lines to massive cables weighing hundreds of pounds per coil, representing the factory's capability to serve maritime, industrial, and construction customers requiring varied rope specifications. The rope industry serves diverse markets, including sailing vessels requiring running rigging and standing rigging for sail operation, cargo handling operations needing strong lines for lifting and securing loads, and industrial applications from mining to construction, where rope provides mechanical advantage through pulley systems. The factory's production capacity and product range determine its market position, with some facilities specializing in marine cordage, while others focus on industrial rope meeting specific strength or handling requirements. The systematic industrial production enables consistent quality and competitive pricing compared to small-scale craft rope making, though traditional hand methods persist for specialized applications requiring characteristics difficult to achieve through factory processes. Inside steam-powered rope factories like this, systematic twisting transforms plant fibers into industrial cordage through mechanical processes that multiply material strength through controlled fiber arrangement. The machinery continues operating, prepared to receive new fiber shipments and repeat the twisting cycle that creates the rope sustaining maritime commerce and industrial operations. Steam power enables the sustained mechanical force necessary for twisting heavy rope, replacing human and animal power that limited traditional rope making to smaller scales. Workers combine traditional rope-making knowledge with mechanical systems operation, maintaining quality while achieving production volumes impossible through hand methods. The transformation witnessed here represents not merely rope manufacturing, but the application of mechanical power to traditional crafts, enabling industrial-scale production while maintaining the fundamental twisting principles underlying rope construction for millennia. Did you know that rope walks were among the longest industrial buildings ever constructed, sometimes exceeding 1,000 feet? If you enjoyed learning about rope manufacturing from the 1850s, please subscribe to the channel, leave a like, and comment about what surprised you most. Your support helps us continue bringing historical industrial content. Thank you for watching. See you in the next video.